We're going to be covering chapter 8.5 through 8.7, and we were introduced to the concept of standard conditions. We're now going to take it a step further and talk about one of the most common calculations, which is standard enthalpy change from tabulated values. You may remember table 8.3. Okay, we're going to talk briefly about bond enthalpy. Remember, enthalpy is actually the energy stored in chemical bonds. And then we're going to finish off with the first law of thermodynamics. All right, let's go ahead and get warmed up with our normal review. Never forget that you can stop the lecture at any time, solve these problems on your own, and then resume to see how I would do these myself. Okay, we're asked to express the standard enthalpy change using table 8.3 to determine the enthalpy of this reaction. Okay, you may recall that delta H naught, the change in enthalpy of the reaction, is equal to the sum of the enthalpies in the products minus the sum of the enthalpies in the reactants. And we're looking at the enthalpy in the 2 aluminum ions and the 3 copper 2 ions. The copper and the aluminum are in their most stable state, and so their values would be 0. Remember, anybody in their elemental state has a value of 0. Okay, and when I put this on my calculator, I generate negative 1256.4 kilojoules per molar quantities. Remember that molar quantities means per the way the reaction is written. Which of the following statements are true? So true or false? Hess's law states that delta H for an overall reaction is the sum of delta H's for the individual equations. This is true. True or false? The molar enthalpy of formation of a compound is equal to the enthalpy change when 1 mole of the compound is formed from its elements. That's pretty much the definition of the molar enthalpy of formation. And then, true or false? A reaction with a negative enthalpy is exothermic. Let's see, negative exo, energy out. This is true. True or false? The enthalpy of formation of an element in its most stable state is equal to 0. This is true. We talked about that a second ago. And true or false, the sum of the enthalpies of formation of the products in a chemical reaction is defined as the enthalpy of reaction. No, it will be the sum of the enthalpies of formation in the products minus the sum of the enthalpies of formation of the reactants. Okay, we're told that methane reacts with oxygen to produce carbon dioxide, water, and releases some energy. And here's the thermochemical equation. And now we're asked what is the value of delta H for 5 grams of methane combusting. Okay, if you're dealing with something other than molar quantities, then we're going to be using our units for this part of the calculation. And that's where we're at. So step 1, we're after delta H, an energy term. Kilojoules would be the appropriate unit. And step 2, I hope you know where we're going to start with the 5 grams of methane. Step 3, out of grams of methane. And again, getting this far should be pretty straightforward. Here comes the big question. Can we go straight from grams of methane to kilojoules of energy? No, we're going to get to kilojoules from moles. So first from grams of methane into moles of methane, so that we can then go from moles of methane to kilojoules of energy. Molar mass of methane is 16.0 grams per each mole. And we're given negative 890.3 kilojoules per molar quantities, and for methane that would be 1 mole of methane. When I put this on my calculator, I come up with negative 278 kilojoules. We should always still be asking, does our answer make sense? The number one thing we want to be looking at is our sign. And indeed, a negative sign does make sense. Okay, acetylene, C2H2, is a gas commonly used in welding. If 2.328 grams of acetylene is combusted in a bomb calorimeter, the temperature of the calorimeter increases by this temperature. If the heat capacity is this number, determine the enthalpy change per mole of acetylene. Okay, well, let's see. First, we're going to calculate the enthalpy change for that 2.328 gram sample, and then we're going to use our units to convert that per mole. Okay, so again, our primary equation, delta H equals Q of the reaction, which is equal to negative Q of the calorimeter. So it's equal to negative big C of the calorimeter times delta T. We are actually given big C and delta T, and do note by an increase of 16.43 degrees C, that's a positive. Note if it said a decrease, that would have been a negative. I then generate negative 116 kilojoules per the sample size. We're after kilojoules per mole. We're going to use our units for this portion. Step 1, we're after kilojoules per mole. Step 2, we're going to start with the just calculated negative 116 kilojoules per that 2.328 gram sample size. We already have our numerator's units, so let's take care of our denominator. So out of grams of acetylene, can we go straight to moles? There's our most common calculation in all of chemistry, so absolutely yes. Twice 12.0 plus twice 1.0 is 26.0 grams per each mole. And that then would be negative 1300 kilojoules per mole. Does the sign make sense? Yes, the temperature of the surroundings is going up, so negative. And the magnitude also makes sense. Okay, we're asked to determine the heat of reaction for the decomposition of 1 mole of benzene to acetylene. And here's that reaction, and that's our main equation. Then we're given these two other equations, and I hope that that reminds you that when you're given multiple equations, that the idea is to add these bottom two together to get our desired primary or main equation. Okay, so how do we do this? Well, first let me identify these for discussion. That the first equation is our main equation, the second is going to be equation 1, and the third will be equation 2. So equation 1 and 2 need to be added together, so we first start with asking, does equation 1 run in the forward direction, or do I need to invert it? So I look to see who's part of my reaction, and benzene is part of it, and it's on the left. I need benzene on the left, so I'm using equation 1 as written. What about equation 2? Well, acetylene is on the left, but I need it on the right, so we are inverting equation 2. And note, by inverting the equation, we inverted the sign. Now, can I add them together as is? Well, let me see, I need 1 benzene, not 2, so I'm multiplying equation 1 by 1/2. And I need 3 acetylenes, not 2, so I'm multiplying equation 2 by 3/2. You know what that does to our enthalpy. When we do add these together at this point, everybody cancels, but 1 benzene goes to 3 acetylenes. All the carbon dioxides, waters, and oxygens cancel. And do note, I now have my enthalpies added together. I already identified that's going to be half of negative 6,271 kilojoules plus 3/2 of a positive 2,511 kilojoules. Next, we're asked to determine the heat of formation of sulfuric acid from the following thermochemical equations. Well, I actually do not have my main equation, so let's put it together. We have sulfuric acid, H2SO4, being formed from its elements. So we have hydrogen plus sulfur plus oxygen forming sulfuric acid. And I'm just going to go ahead and balance this. And I come up with H8 hydrogens, 1 octasulfur, 16 oxygens to form 8 sulfuric acids. Okay, so let's go and look at our equations. And so again, we'll let the first one be 1, second one 2, third one 3, and fourth one 4. Okay, what do we do with equation 1? Well, octasulfur is on the left, so looks like we're going to use equation 1 as written, but we notice that in equation 2 we have octasulfur as well. So which one are we using? Well, only one of these has a product that can cancel with another reaction, and that's the sulfur trioxide. So we're using equation 2, not equation 1. And octasulfur needs to be on the left, so we're using it as written. In equation 3, sulfuric acid is on the right, and I need sulfuric acid on the right, so I'm using equation 3 as written. In equation 4, I need hydrogen on the left. So far, nobody's had hydrogen, so we need to use equation 4 as written as well. Okay, I need 1 octasulfur, so for my, what would be equation 2, S8 plus 12 O2s goes to 8 SO3s. I need 1 octasulfur, so I'm going to use equation 1 as written. In equation 2, I need 8 sulfuric acids, so I'm going to multiply that by 8. And in our last equation, we need 8 hydrogens, so we're going to multiply that last equation by 4. And again, do note, by multiplying each of these by some coefficient, we're multiplying the enthalpy by that same coefficient. And sure enough, everybody canceled to give me my desired equation. And there's my enthalpy. Now I'm entering the enthalpy of formation, which means I need just one sulfuric acid, so I'm going to rewrite that by multiplying the whole thing by 1/8, which means that our enthalpy is multiplied by 1/8. Okay, we're asked to use molar enthalpies of formation to determine the heat of combustion of 1 mole of glucose, C6H12O6. Okay, well, we need the chemical reaction, and so we have glucose reacting with oxygen to form carbon dioxide and water. Remember, any combustion reaction, we have our organic compound, plus O2 goes to CO2 and H2O, so that portion of the reaction is always the same. Okay, and to balance this is the coefficients that I come up with. And so the enthalpy of a reaction is the sum of the enthalpies in the products minus the sum of the enthalpies in the reactants. So we're looking at the enthalpy in the 6 carbon dioxides and the 6 waters minus the enthalpy of the glucose. We're given all those quantities, so we plug them all in. And do note we have to take into account those coefficients. And I come up with negative 2802.5 kilojoules per the mole quantities based on the way the chemical reaction is written. Does our answer make sense? Well, I definitely expect a negative enthalpy change. I expect energy being released when something is undergoing combustion. Okay, on to new material, and first we're going to talk about the calculations of standard enthalpy change, represented as delta H naught, and we've already got kind of start on this with what that naught means. The 0 refers to standard conditions. And I hope you recall that. Standard conditions are 1 atmosphere pressure for anybody in the gaseous state, 1 molar concentration for anybody in the aqueous state, and then 1 mole quantity for anybody in their pure state. Okay, let's look at an example where we're asked to express the standard enthalpy change for the combustion of 1 mole of propane. Well, let's go ahead and write out that reaction. There's propane, and remember the rest of the reaction is the same. Plus O2 goes to CO2 and H2O. Again, that part of the combustion reaction is always the same. Okay, so the standard enthalpy change is, well, actually, I need to balance this, so let me go back and do so. And remember, we begin by asking, is there anybody that should be left for last? And that would be the oxygen. So we start with carbons, 3 on the left, 1 on the right. Least common multiple is 3. Whatever your least common multiple is, that's how many go on both sides. Then hydrogen, 8 on the left, 2 on the right. The least common multiple is 8. So let's put 8 hydrogens on both sides. And now I'm going to count my oxygens on the right and force the O2 on the left to balance. If it's odd or even, I'm going to force that O2 to balance. Okay, 3 times 2 is 6, 4 more is 10. Yay, that's an even number for 5 O2s. Remember, if this was a fraction, or excuse me, if this was like 9/2, an odd number, I would write the fraction 9/2 and then multiply the whole equation by 2. Okay, I didn't have that, so on to the calculation. Our standard enthalpy change, delta H naught, is equal to the sum of the enthalpies in the product, so the 3 carbon dioxides and 4 waters, minus the enthalpy in the reactant, so that's going to be the 1 propane, since the enthalpy of formation of the oxygen is 0. I'm going to go ahead and carry that just to make that point. Okay, so here's the standard molar enthalpies of formation for the carbon dioxide, water, propane, and oxygen, which gives me a value of negative 2219.9 kilojoules per the way the reaction is balanced. Again, does the answer make sense? And that negative surely does, and I would expect a big number for the enthalpies associated with combustion. Okay, the thermochemical equation for the combustion of benzene is given here. And we're asked to calculate the heat of formation of benzene. Okay, well, what we're going to find here is we're going to set up the calculation for the enthalpy of reaction. go ahead and do that. Delta H naught equals heat of formation of the 6 carbon dioxides, the 3 waters, minus the heat of formation of the acetylene, the benzene, and the oxygens. This time I'm going to go ahead and put in 0 for the oxygens, and put in what we know. We actually have the enthalpy of the reaction, so at this point it's really just a matter of math. Let's solve for the enthalpy of formation of the benzene, and then plug these numbers into our calculator. And I come up with 49.0 kilojoules. Does our answer make sense? And it's really hard to tell at this point if I've made a simple mistake. Nothing obvious is jumping out as incorrect. So many times we have clues about the signs. That was an example where we really didn't. Okay, next one, hydrochloric acid is added to a solution of sodium carbonate. Hydrogen dioxide, carbon dioxide is formed. This is essentially very similar to the reaction of vinegar and baking soda, by the way. And now we're asked to calculate delta H for this thermochemical equation. Okay, the enthalpy of reaction, delta H naught, is equal to the sum of the enthalpies in the product. So that's the 1 carbon dioxide and the 1 water, minus the sum of the enthalpies in the reactant. So that's the 2 hydrogen ions and the 1 carbonate ion. Do note that the hydrogen ion is the only ion that has an enthalpy of formation of 0. There will be other times in our future where we'll see where the hydrogen ion has a value of 0, how it actually acts almost like a standard 0 point. We'll see those in the future. I'm actually talking about Chem 112, where I hope you join us. And let me go ahead and put that on my calculator, and I generate negative 2.2 kilojoules, and I would ask again, does my answer make sense? And it's hard for me to really tell if energy was released or consumed, and if it was going to be a lot or a little, so it's really hard for me to tell if that answer makes sense. I can always double check by putting this on my calculator, but that still wouldn't catch all the mistakes that could potentially come up. Okay, on to bond enthalpy, and remember, enthalpy is energy stored in chemical bonds. Now, bond enthalpy is actually defined as the energy that's required to break 1 mole of bonds when we're breaking those bonds in the gaseous state, so that we're not really worrying about other participants contributing here. And so here we see to break apart 2 hydrogen atoms from the hydrogen molecule, it takes 436 kilojoules. To break the 2 chlorine atoms away from a molecule of chlorine, it takes 243 kilojoules. We've already discussed how breaking bonds takes energy, so that's why it always takes some energy to get a chemical reaction to occur. And so this should totally match that. That breaking bonds is going to always be a positive value, a positive energy. We have to pump energy in to break those bonds. So what would that mean if we went the other way and formed those bonds? Well, ultimately, we're going in the opposite direction, and we know what happens when you invert an equation. Our enthalpy is equal in magnitude, but opposite in sign. So here we can see how if hydrogen chloride separate hydrogen and chlorine, we have positive 431 kilojoules. But if the hydrogen and chlorine come back together to form hydrogen chloride, it releases that same 431 kilojoules. I hope this totally makes sense, as it totally matches what we've been learning all along. So real quick, breaking bonds, positive enthalpy. Forming bonds, negative enthalpy. At least a negative and positive for changes. Don't forget that change. That actually is the key word. Okay, now we can actually use these bond enthalpies to give us some explanation as to why some reactions are endothermic or exothermic. Now let's look at some reasons or some explanations as to why a reaction might be expected to be exothermic. First, we might expect that the bonds in the reactants are stronger than the bonds in the products. Remember, if there's more energy in the bonds of the reactants, we had to pump more energy into it than we got out of it. In addition to this, we might have a scenario where we simply have more bonds in the reactants than in the products, because more bonds means more energy. It also should make total sense that if we have multiple bonds, that they're going to have more energy than single bonds. And do note here for carbon, carbon-carbon single bond versus a carbon-carbon double bond and a carbon-carbon triple bond, that we're having an increase in bond enthalpy with an increase in the number of bonds. And that should totally make sense. You have to break more bonds to get through. Okay, let's look at some example calculations. Now, these are going to look a little bit different than the enthalpy change calculations that we've done before. The reason for that is, in the past, it's been your delta H naught is the sum of the enthalpies and the products minus the sum of the enthalpies and the reactants. If you do this in that fashion, you're going to have the right answer, but with the wrong sign every single time. Why would that be? Because we need the subtraction, the negative, to be with the enthalpies and the products. And the positive needs to be associated with the breaking of the bonds and the reactants. Now, there are several ways that we can get through this. One is to just go backwards and take the enthalpies and the reactants and subtract the enthalpies and the products, or we can just remember the signs and just add them all together. Breaking it, we know it's positive. Forming it, we know it's negative. Okay, so we're asked to calculate the enthalpy formation for the combustion of hydrogen, and here's the balanced equation. Okay. Now, the enthalpy of the reaction, delta H, is going to be equal to the enthalpy in the 4 OH bonds that are formed. So that means that enthalpy value is negative, so note that negative sitting in front of the delta, plus the enthalpy involved in breaking the 2 hydrogen bonds, and we're breaking it, so that's why it's positive, plus the enthalpy associated with breaking the double bond in the O2, and again, note that's positive because we're breaking it. So we just went ahead and added them all together, knowing that the enthalpy in the products is going to have a negative value, the enthalpy in the reactants is going to have a positive value. Okay, so again, enthalpy associated with forming bonds, negative. Enthalpy associated with breaking bonds, positive. And when we calculate my answer and I come up with negative 486 kilojoules, I should still be able to have some idea if the answer makes sense. Well, in combustion, energy is being released, so that negative certainly makes sense. Do note the way we set up this calculation, significantly different than the way we've done those past calculations. Okay, on to the first law of thermodynamics, and you may recall talking about delta H was equal to Q when we're not doing work. Well, the reason for that is that the total energy, the change in energy for the whole system, would be equal to the enthalpy change for the system plus any work that's done by the system, or done on the system, I should say. Now, I would point out that the work is actually equal to the, now this is only for gases, that the work of a gas is equal to the pressure of the gas times the volume of the gas. And if you're doing this work on the surroundings by expanding, then that's going to be a negative value. Again, work is being done on the surroundings. You're actually releasing work, and so releasing energy, negative. Now, the relationship between delta H and delta E is, well, remember, delta H was equal to the enthalpy of the, Q of the reaction when we weren't doing work. And so the energy is equal to the enthalpy plus the work, which means minus PV, because remember the work is equal to negative PV. And so that's the relationship between the enthalpy and the energy, or the change in enthalpy and the change in energy. We might rearrange this to get H is equal to E plus PV. And again, normally we're interested in a delta, the change. And so delta H is equal to delta E plus delta PV. So if you're changing your pressure and changing your volume, you have a change in your, or essentially you're doing work. Pressure is held constant, volume is held constant, then we're not doing any work. Okay, now I would remind you that PV equals nRT, back from the chapter on the gas laws, and so our change in PV is actually equal to our change in nRT. What we're really looking at is our change in the number of gas molecules. So let's go ahead and see how much energy is associated with this change in gas molecules. I'm going to do it for just one gas molecule. And so for forming one gas molecule, do note using nRT, R being the universal gas constant in units of kilojoules per mole Kelvin. Of course, our temperature has to be in Kelvin. A mere 2.5 kilojoules is associated with the work done with the formation of 1 mole of gas. That's not a lot of energy. So, for the most part, there's going to be a very minor difference between delta E and delta H, usually significantly less than 1%. That doesn't mean we're not going to do some calculations where we're bringing in the work. But just to make it clear, normally we don't have to take that into account. And this is why. Okay, let's look at an example. We're told to calculate delta E for a gas for a process in which the gas absorbs 25 joules of heat. What's going to be the sign of the energy if it's absorbing 25 joules of heat? And does 7 joules of work by expanding. What's going to be the sign of that 7 joules of work if it's expanding? Well, first, delta E is equal to Q plus W, and is that a positive 25 or a negative 25? You're absorbing 25 joules, so that's positive. What about that 7 joules of work done by expanding? You're doing work on the surroundings, and hence that's negative. For a total change in energy of 18 joules. Okay, we're asked to calculate delta E for a gas for a process in which the gas evolves 12 joules of heat and does 8 joules of work by expanding. Okay, again, delta E is equal to Q plus W, and is that a positive 12 joules for the heat, Q, or is that a negative 12 joules? Well, if you're evolving it, you're releasing it, and I hope you know that means that it's negative. Again, we're doing work on the surroundings by expanding, so again, W, our work, is negative. And hence our delta E is negative 20 joules. Okay, let's practice some of the things that we've gone over. All right, the thermite reaction is an exothermic process that yields iron metal as a product. Here is that balanced thermochemical equation. And actually it doesn't give us the enthalpy for the reaction, so I do that. And now, using enthalpies of formation, determine the heat release when 5 grams of the iron 3 oxide reacts with excess aluminum. Okay, we have two parts to this problem. I hope you can see it. The first is to calculate the enthalpy of the reaction, and then we're going to use that energy per mole to then calculate the energy for that 5 grams, and we'll use our units for that portion. So again, we begin with the equation. Delta H naught is equal to the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants. You probably don't need to write that down by now. So we're looking at the heat of formation of the 1 aluminum oxide minus the heat of formation of the 1 iron 3 oxide. And you know why aluminum and iron fell out of that calculation. Let's bring out the numbers and put it on our calculator. And I come up with negative 851.5 kilojoules. Does that negative make sense? Yes, this is an exothermic process, we're told. Okay, that's the first part of our calculation. We're using our units for the second, where we're going to be after kilojoules per 5 grams. So step 1, we're after kilojoules. Step 2, we're starting with the 5 grams. And now step 3, out of grams of the iron 3 oxide. Can we go straight from grams of iron 3 oxide to kilojoules of energy? No. How are we going to get to kilojoules? Or moles. So first into moles of iron 3 oxide. And then from moles of iron 3 oxide, we can go straight to kilojoules. Molar mass of iron 3 oxide, 159.7 grams. Molar mass, and then negative 851.5 kilojoules per each mole of iron 3 oxide. And when I put this all on my calculator, I generate negative 26.7 kilojoules, and when I ask does it make sense, it seems like it does. At least asked. Sometimes we can tell, sometimes we can't, but at least asked, does our answer make sense? That's just the beginning of critical thinking. Okay, next we're told glucose reacts with oxygen to release carbon dioxide and water, and there's the balanced chemical equation. And we're asked what mass of glucose must react to release 1,000 kilojoules of energy. Okay, well this is also going to have two parts to it. First we need the enthalpy of the reaction, so we're going to use an equation to calculate that. Then we're going to use that along with our units in the second part of the calculation to calculate the mass of the glucose to release the 1,000 kilojoules of heat. Okay, so similar to the last problem, and so first delta H naught of the reaction is equal to the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants. So that's the heat of formation of the 6 carbon dioxides plus the heat of formation of the 6 waters. You note it's in the liquid state. I've got my my abbreviation here incorrect. Minus the heat of formation of the glucose. Let me go ahead and grab those. Again, these were all given in the problem. And that gives me the enthalpy of reaction. That's the first thing we need to do. The second thing is to use our units to get our actual answer. If you're dealing with non-standard conditions, then we're going to be using our units for that portion. Step 1, what are we after? The mass of glucose. Step 2, what are we going to start the calculation with? 1,000 kilojoules of heat. And do note it's negative. Why did I put the negative in there? Because we're told that it was released. Now step 3, out of kilojoules. Here comes the big question. Can we go straight from kilojoules to grams of glucose? No. From kilojoules we're going to go to moles of glucose. And then from moles of glucose we can go to grams. Okay, that's negative 2,802.5 kilojoules per each mole of glucose. And we have the formula there to come up with the molar mass, 180.0 grams per each mole. So that 1,000 kilojoules takes 64.2 grams. Does our answer make sense? And I'm going to say it really does. Okay, which of the following statements are correct? So true or false, the formation of a bond is an endothermic process. The breaking of a bond is endothermic. You need to supply the energy to break the bond. The formation of a bond is always exothermic. True or false, the bond energy of a multiple bond is greater than that of a single bond. True. True or false, bond energies between two different atoms are approximations. I didn't mention this, but this is actually true. True or false? The energy required to break a bond is positive. This is true. You've got to put energy in to break those bonds. True or false? A reaction is expected to be exothermic if the bonds of the products are stronger than those of the reactant. And this would be true. Just think of which side is going to have the bigger number. What the side with the bigger number would be the side that's going to be negative. And the side that with the bigger number being negative is the side where bonds are being formed. So a reaction is expected to be exothermic if the bonds of the products are stronger than those reactants. This is true because, again, if the bonds of the products are bigger numbers, and we're subtracting the bigger numbers to give us a negative answer. True or false? In a chemical reaction, the change in energy of the system and the surroundings are equal in magnitude but opposite in sign. This is true. True or false? An expanding gas does work on the surroundings, thus W has a negative value. This is true. And true or false? Delta E equals Q plus W, where Q is equal to heat and W is equal to work. True. And if a reaction occurs at constant volume, then Q is equal to delta E. Well, if your reaction is at constant volume, that's essentially saying that work is not being done. And hence, yes, true. And true or false, if a reaction occurs at constant pressure, W is equal to delta E, and this is not true. I hope you can see that definitely is not true. Okay, if not handled carefully, ammonium perchlorate can decompose violently according to the thermochemical equation below. And now the enthalpy of formation of water is given. Now we're asked to calculate the enthalpy of formation of ammonium perchlorate. Do note we only need to be given the enthalpy formation of the water because everybody is in its elemental state. Okay, our primary equation, remember we always start with the primary equation, delta H naught equals the sum of heat of formation of the product, so that's the 4 waters, minus the sum of the heat of formation of the reactant, so that's the 2 ammonium perchlorates. Remember, all those other guys in the elemental state just fall out of the expression. And we're given the thermochemical equation, meaning the value for the delta H, and so we can plug that in for delta H naught. Let's plug it in the given values for the heat of formation of the water. And at this point, we're solving for the heat of formation of the ammonium perchlorate. Here I've just rearranged my equation to isolate that variable. I would point out, and this is what I would normally do, I would normally isolate my variable symbolically and then bring in the numbers. So you don't have to write the numbers multiple times. Okay, let's crunch those numbers, and I come up with negative 295.8 kilojoules per molar quantities. Does our answer make sense? Well, for one, energy should be your energy should be negative since it is being released. Essentially, the environment is heating up, and if you're reacting explosively, then energy is being released in that action. So yes, the negative makes sense. What about that magnitude, 295.8? I can't really tell. So I'm just going to go with, yes, this makes sense. Okay, now we're asked to use molar enthalpy formation to determine the heat of reaction for the combustion of 1 mole of methanol. Okay, our primary equation, delta H naught equals the sum of the heats of formation in the products minus the sum of the heats of formation in the reactants, and I doubt you need to write that out anymore. So you probably want to just jump down to the heat of formation of the 2 carbon dioxides plus the heat of formation of the 4 waters minus the heat of formation of the 2 methanols. Let's grab those numbers and put them on our calculator. And I come up with negative 1452.8 kilojoules. Does that negative make sense? Yes, it's burning. Energy is being released, so yes, that negative makes sense. All right, that's per molar quantities, which would mean per 2 moles of methanol, not 1. I think we can see we're essentially dividing this by 2, but let's use our units. Step 1, we're after the enthalpy change, so kilojoules. Step 2, we're going to start with the 1 mole of methanol. Step 3, from moles of methanol, we can go straight to kilojoules. That's negative 1452.8 kilojoules per 2 moles of methanol. And so indeed, as we already said, take that enthalpy change, which was for 2 moles of methanol, and divide it by 2. We don't always have such nice easy numbers, so having a reliable method like what we're just shown is something we need to carry around with us. Okay, that concludes this lecture, where we took standard conditions a little bit further. And whenever you're after standard enthalpy changes, normally you're going to be given standard enthalpies of formation. Either you'll be given table 8.3, you'll be given that information within the problem, as we've seen in several examples. Bond enthalpies were for individual bonds. This doesn't have nearly as practical application as the standard enthalpy change calculations that we did earlier. And so I just want to point out this is not nearly as common. So we're not going to see as many examples of bond enthalpy as we just saw. And for future exams, don't expect a whole lot of questions along those lines. Definitely lots and lots and lots about calculate the standard enthalpy change for this reaction, where you're going to be given table 8.3. Then the first law of thermodynamics essentially stated that the energy of the surroundings and the system are equal in magnitude but opposite in sign, and we had to take into account that some of that energy shows up in the form of work. Okay, that concludes this lecture.